Okay, so we're picking up with part 2 of chapter 10 here, looking at gases and the ideal gas law. The previous part, we had just went through how to, our initial use of the ideal gas law and this important value of 22.4 liters. And so let's take a look at an example of stoichiometry with some gas problems here. And so the question's asking, we have 1 liter of oxygen and an excess of octane. What volume of CO2 will be produced? So a couple of key things to point out before we even start doing some math. So you'll note that I tell you guys that we have an excess of octane. Now, what should that mean for you? Well, remember, uh, just because we're not in the chapter where we talked about limiting reactants doesn't mean we can't have limiting reactant problems in this chapter, right? So again, when you see this flag of the term excess, right, we're saying, hey, don't worry about limiting reagents. I am telling you what the limiting reagent is, right? If we have an excess of octane, that means the oxygen has to be the limiting reagent, okay? So it tells us we have 1 liter of O2, so we have 1.0 liters of O2, and it asks us how much CO2 will be produced, right? So we need to figure out that. This question is basically the same as if I had asked, what if we have 1 mole of oxygen, how many moles of CO2 will be produced? Right? If you go back to part 1, we talk about one of the laws, or one of the, maybe not laws necessarily, but let's say one of the assumptions that we make, and it's the law of combining volumes here, right? For an ideal gas, volume is proportional to the number of moles. So for us, when we're talking about volumes of an ideal gas, it's almost exactly the same as dealing with moles. So this could read, in essence, if I have 1 mole of oxygen, how many moles of CO2 will be produced? So to do that, right, I take 1 mole of O2, or excuse me, 1 liter of O2, right? That means I have to cancel out liters of O2 on the bottom and convert this into liters of CO2, right? So essentially the question is now asking how many liters of O2 produce, produce how many liters of CO2? And for that, we look at our stoichiometry here, right? 25 liters of O2 makes 16 liters of CO2. And that's all this question is really asking, right? It's just an example of showing how stoichiometry is brought into the gas law problems here. And if we do this, I got 0.64 liters of CO2 produced. Okay. So go back in part 1 there, you'll see what we're talking about with the law of combining volumes, or a simple way of looking at it is just, how do gases behave with stoichiometry? So a topic to talk about here real quick, density and molar mass. So if we take our ideal gas law, right, if we take PV equals nRT, right, and we do some rearrangement, right, we divide by RT and we divide by volume, right, we can get from here to here, right? If we then multiply by the molar mass M, right, we multiply both sides by the molar mass M, right, we get this new expression here, which simplifies into density is equal to the pressure divided by molar mass, pressure times molar mass times the ideal gas constant R times temperature. Okay? And you say, I'm not sure how this works. Well, let's take a look at this here, right? So let's take a look at this side right here, right? So N is moles, so moles times the molar mass, right? So molar mass is moles, right, typo there, grams per mole, right? Molar mass M here is grams per mole, and we divide everything by volume, right? V. If we look at our units, then moles cancels out with moles, and so that whole side in green over there simplifies to grams over volume, right? Equals PM over RT. Got it? So this side in green here, right? This in green is that part right there. And if we have units of grams over volume, right, such as grams per milliliter or grams per liter, et cetera, grams per cubic centimeter, that is units of density, right? This is density. So we can use density to help us out with some of the equations. And now we also have a relationship for molar mass. So if you take a look in your book when it's asking you to figure out kind of molar mass of some unknown gas, right? This is a new equation that we're going to have to use here, which is just a derivative of the ideal gas law. Okay. Right. Here's just another, showing of what we just did, right, to get to the same point. And basically what we're seeing here is density is proportional to the molar mass, right? The heavier something is, the more dense it is. And that shouldn't be too shocking, right? It shouldn't be too shocking because the units of density is based directly off of mass, right? So if something's heavier, it should make sense that it's more dense, right? If something weighs more, right, it should make sense that the density increases also. That's probably not too much of a surprise to you guys, though, at this point. Now we get to kind of the crux of the matter, something known as the combined gas law, right? The combined gas law is um, probably one of the most useful uh, ideas or equations that we can use. And the combined gas law basically works like this: P1 V1 over N1 RT1 is equal to P2 V2 over N2 RT2. Okay? So the combined gas law is basically stating what happens to a gas as we change some factor, as we either change pressure or volume, moles or temperature, right? A combined gas law is what we're going to do if we say, how do we have something initially, right? What is happening initially, and how it changes to some final conditions, right? Now let's see if we can simplify this just a bit, right? You'll notice that R is in both sides of this equation. So we can just get rid of that. Well, how do we know that? Well, R is a constant. If it's a constant, it can never change, right? So even if as we're dealing with changes, right? So as we're dealing with system, right? As we're dealing with changes to our system or the gas that we're looking at, R, right, cannot change. But it is a constant. So essentially, it's going to be the same on both sides, so we can just get rid of it, right? And so our equation simplifies to P1V1 over N1T1 equals P2V2 over N2 and T2. All right, so this is the equation, right, that we're talking about with a combined gas law here. So how do we use this? Well, let's take a look at an example, okay? A gas occupies 401 milliliters at a pressure. What will its volume, what will be the new volume, right, if the pressure is decreased and held at constant temperature, right? So let's take a look, right? P1V1 over N1T1 equals P2V2 over N2T2. Okay? So what information are we given? Well, we're given volume, right? We're given V1, right? 401 milliliters, right? We're given P1, 1.00 atmospheres, right? It says the pressure is decreased, right? So P2 equals 0.75 atmospheres, right? And it asks us what will the volume be, right? So we need to figure out V2. So we have information about V1, check. We have information about P1, check. We have information about P2, check. We need to figure out V2. It tells us that temperature is constant. So what does that mean for us? Well, it means that T1 is equal to T2, right? And if it's a constant, then we can just get rid of it in our equation. We also have to assume that the number of moles is constant. Otherwise, this would be a different problem, right? It would have to give us some information about that. So we have to assume that N1 is equal to N2, right? Okay, so N1 and N2 are constant. And so we take our big scary equation down to an equation with 4 parts, right? And we have information about 3 of those, right? So 401 milliliters times 1.00 atmospheres, right, equals 0.75 atmospheres times our V2. And if we do that and we solve for V2, I got about 535 milliliters. Okay. And you might say, well, wait a minute. This kind of looks familiar, right? P1 V1 equals P2 V2. Well, that's Boyles Law, right? That's Boyles Law. And if you go back to the slide in part 1 where we talk about Boyles Law, it says, well, temperature and moles must be held constant. Well, here you go, right? So we just basically used Boyles Law, and we kind of, let's say, derived it, just by looking at one of our combined gas law equations and working from there. Okay? All right. What volume will 2.64 moles of N2 occupy at 0.64 atmospheres and 31 degrees Celsius? Okay? So we're given a problem. Let's start to write out what we have. We're given N. N is equal to 2.6, sorry, let me rewrite that, 2.64 moles, right? We're given pressure, 0.64 atmospheres, right? We're given temperature, 31 degrees Celsius, which is equal to 304.15 Kelvin, right? Remember, we have to do everything in Kelvin. We are asked to figure out volume, right? So volume is our question mark. And as always, we're given R. We just have to pick the right R. We're given atmospheres and moles, right? So we can just pick 0.082, right? Liters, atmospheres, mole, Kelvin, right? So just pick the right gas law to match your units in this case, right? We know our equation because that's really not going to change, right? For this chapter. So we take PV equals nRT and we solve for V. So V is equal to nRT over pressure. And we fill in the blank, right? So volume is equal to N, 2.64 moles, R, 0.082 liters, atmospheres, mole Kelvin, times temperature, 304.15 Kelvin, divided by pressure, which was 0.64 atmospheres. Plug and chug, right? Plug everything into your calculator. Volume equal to 103, about 103 atmospheres. Oops, I'm sorry, not atmospheres, liters. I apologize. Wrong units. 103 liters. Not too bad, right? Simple execution of PV equals nRT. The big trick to these problems is getting a table of information, right? Get a table of information, write down what you have, and then see how it plugs in to your equation. All right. So 100 grams of octane burns at standard temperature and pressure. What volume of O2 will be consumed, right? What volume of O2 will be consumed? So this one's a little bit trickier here, right? This one's a little bit trickier here. So now we got to think a little bit. Well, it's asking us how much O2 will be consumed, right? So we need to figure out how much of this stuff uh, disappears, so to speak, or how much of that stuff gets used up, right? And it tells us information about octane, right? Octane is this guy over here, right? So it gives us information about both of our reagents. So this is a limiting reagent type problem. And it's basically asking us how much oxygen do we need to completely react with 100 grams of octane, right? So this is essentially a limiting reagent problem. So we need to find a way to relate methane to O2. Now, first of all, immediately when you guys see grams at this point, you should know that grams are mostly useless to us, right? Grams are not really going to be useful. So um, we need to convert grams into moles, right? So step one, grams into moles. So 100.0 grams of octane, C8H18, 114.2 grams for every 1 mole, and so 0.8754 moles of octane. Okay. Now we need to do limiting reagent, right? Limiting reagent comparisons, right? We need to figure out how much O2, right? How much O2 is it going to take to react with that many moles of C8H18, right? So essentially, what we need to do is convert moles of, sorry, I meant to do that a little bit bigger. We need to convert moles of octane into moles of O2, right? So the first thing we did was grams into moles. The next step is moles into moles, a very common step that we've done before in limiting reagent problems. So here's how it looks, right? 0.8754 moles of octane. We convert moles of octane into moles of O2. Right, 25 up here, and oh, let's do this in green, right? 2 here, right? For every 2 moles of octane, we consume 25 moles of O2. And if we do that math, we will end up with 10.94 moles of O2. Let's do the last step in blue then. Now the last step is the question asks us what volume of O2, right? What volume of O2? So we need to convert moles into volumes. And you say, well, how in the world are we going to do that? Well, here is big red flag, right? We're doing this at standard temperature and pressure. At standard temperature and pressure, 1 mole of gas is equal to 22.4 liters. I should be very careful here. Yeah, 1 mole of a gas, I should say here. 1 mole of gas is equal to 22.4 liters. So if we take 10, oops, wrong size, 10.94 moles of O2, and we use our conversion, for every 1 mole of O2, we have 22.4 liters, right? That's about equal to 245 liters of O2. So I had to give you information about temperature, right? Pressure, right? Temperature and pressure to be able to do this conversion, right? That's what standard temperature and pressure tell you. You can see similar problems like this where I tell you 100 grams of octane burns at 30 degrees Celsius at 1 atmosphere, right? If I give you information about temperature and pressure, that's different from STP. So if not at STP, use ideal gas law, right? If I give you information about temperature and pressure, that's different than STP. You have moles, then you have information about temperature and pressure, you have your gas constant, and you can calculate for volume, right? Technically speaking, behind the scenes here, we are doing the ideal gas law. We're just doing a simplified version of it. Now, if you're like, what in the world is he talking about? Well, back up. I think it was in part 1 where we worked through how to get that 22.4, right? But if I give you information different than STP, use the ideal gas law to solve this, okay? So let's take a look at this problem here then, right? What volume of O2 at a specific pressure, at a specific temperature, will react with 10 moles of octane? Right? So almost exactly the same as previously, but now we have some additional information. Pressure equals 752 torr, okay? Temperature equals 25 degrees Celsius, right? AKA 298, right? Kelvin, or 298.15, either way is fine. We'll go ahead and add in our constant R. We're using units of torr, right? So we need the 62.3 liters torr mole Kelvin, right? So we need that constant R there. And it's asking us to figure out volume, right? Volume of O2. So the only thing we're missing right now is moles, right? It gives us information about moles of octane. We need to figure out moles of O2, right? So let's figure out what color do we want to do this in? We'll do it in black, right? We need to figure out moles of O2. So we have 10.0 moles of octane. We convert that into moles of O2 for every 2 moles octane, 25 moles O2. 125 moles of O2 sounds great, right? Now we can take that and plug it in over here, right? So I'm just going to take that value over here to our table. Not 150, 125. Good stuff. Now we have a nice complete set of information that we can use in our ideal gas law, right? PV equals nRT. We rearrange for V, right? nRT over P. And now we just plug everything in. So equals to 125 moles. We bring in our value of R, 62.3 liters torr mole Kelvin. Temperature, 298 Kelvin, divided by pressure in blue, so 752 torr, right? And if we do this, right, volume then is equal to, I got 3.09 times 10 to the third liters. So basically 3,000 liters there, right? 3,090 is what we could say. And again, why did we have to do it this way? Because we're not, right, at STP, right? We're not at standard temperature and pressure. So we can't assume that it's that the volume is equal to 22.4 per mole. So we have to use the ideal gas law in this case. All right. Now let's look at an example of density here. Right? So we have 1 liter flask contains that many grams of unknown gas at that pressure and at that temperature. Right? And so we're asked to determine its molar mass here. Okay, so let's think about what we need to do here first, right? Let's gather our information. We are given that volume is equal to 1.00, right? Volume. We're given pressure, 0.850 atmosphere, right? We're given temperature, okay? We know our value of R, right, based off of our units. Liters, atmospheres, mole Kelvin. Okay. So what do we not know about? Well, we don't know about moles. Well, that kind of makes sense here, right? It asks us about molar mass, right? So molar mass, right, is equal to grams over moles. Oh, well now it starts to hopefully click together. We know how many grams we have, so we can fill that in. And if we figure out moles, right, we can divide grams by moles to get our molar mass. So let's take a look at our ideal gas law, PV equals nRT. Let's rearrange to solve for n, right? So n is equal to PV over RT. So now let's plug and chug, right? So n is equal to pressure, 0.850 atmospheres, volume, 1.00 liters, over R, 0.08206 liters, atmospheres, mole Kelvin, times temperature, 293.15 Kelvin. And if I do this math, I got n is equal to 0.03533 moles. So finally, our molar mass is equal to 1.13 grams divided by, right, 0.03533 moles. And so I got molar mass equal to 32.0 grams per mole. And the only gas that we know of so far, or one of the most common ones that we know so far with 32 grams per mole, is O2. Right? So our molar mass is 32, and this is probably oxygen, what we're dealing with here. So again, the big secret, although it's not really a secret, is make a list of what information you have and look at what's missing, right? Look at what's missing and then basically solve our ideal gas law for what's missing, and then what do we need to do with it. This seems like a good place to pause. It's a nice break point in the lecture, and so we'll pick this up, and I think we'll finish up next time with the rest of chapter 10.